Going further with the story of Taylor polynomials and remainders, we just recapping what we have for the second degree, or also called second order Taylor approximation, and the error estimate that we just got. And I want to do an example, two variations of an example on cosine x. You really want to look at a lot of examples at this point, but I don't want to put it all on video and kind of bog down the exposition. So we're going to look at cosine x again. And it looks like this. And we're going to look at that quadratic approximation, and we're going to see what we can get out of this error estimate in two cases. So first of all, we know that f prime of x is minus sine x, f double prime of x is minus cosine x, and we're going to need the third derivative, but of course that's just back to sine x. And what's wonderful about this particular example is that these functions are so familiar and are easy to bound. But for right now, we just need that, well, of course, f of 0. We're going to do it around 0 for simplicity. That's equal to 1. F prime of 0 is equal to 0. F double prime of 0 is equal to minus 1. It's concave down at the point we're interested in. And we don't really care just about f triple prime at 0. We're really going to have to be a little bit more subtle about our analysis of that. So I'll save that for a sec. But these are the ingredients that go into the T2. And so I'm going to just take it all the way up here. And we get for cosine at 0, we just get 1 plus 0 times x minus 0 minus 1 over 2 times x minus 0 squared, or 1 minus 1/2 x squared. So that's a nice parabola. Looks like this. Okay. So there's our quadratic Taylor approximation. Clearly, because it's a parabola, it can't do an exact match for very long of this wiggly function that turns around. But it's actually pretty good in here, and I'll show you some computer plotted pictures in a minute. But let's just go ahead and get an error bound. Suppose we didn't have the computer to take a look and didn't know how to evaluate cosine carefully and wanted to get some idea of how good this was. So first version would be we could use a universal bound. This is pretty uncommon, kind of special to like sine and cosine examples, on the size of the triple prime, the third derivative, because, of course, since that's sine of x, we happen to know that's always less than or equal to 1, the absolute value. Okay, so we can make that our m value if we want. Okay, so that means that the size of the remainder in the quadratic approximation will be guaranteed to be less than 1 over 3 factorial, or 1 over 6, times absolute value of x minus a, well, that's just x here cubed. Okay, so that's cool. So that's interesting. No matter how far you go from 0, this is a little bit unusual because we could use this universal bound that was true for all x. Let me emphasize that. For all x, we can say that the remainder is always less than or equal to 1/6 x, absolute value of x cubed. There's a good and a bad side to that, and it's very, very common. When x is smaller than 1, especially when it's quite small, cubing it is a really good thing, makes a really small number, and tells you that this is actually pretty darn close. When x gets bigger than 1, especially if x is rather large, the cube hurts you and tells you that, in fact, the difference between this approximation, oh, I should have done a different color, the difference between this quadratic approximation and the real thing is, not surprisingly, horrible. It's not guaranteed to be particularly good at all. And that's exactly what you expect from this kind of thing. This is not a polynomial globally, and so we would be crazy to expect it's a good approximation globally when x is large. So this shouldn't tell us anything that is obviously not true. But when x is small, it's telling us something very, very useful. And in particular, as soon as x is decently smaller than 1, this is pretty good. For example, if like x equals 0.1, it's telling us that at worst, and again, this is always worst case scenario, it could quite well be better. And this, for example, it turns out for cosine, it's quite a bit better. for good reasons that we'll come to later, this would be less than 1/6 times 1/1000, 1 over 6,000. That's pretty good. That's a few decimal places from a very, very primitive approximation. Now, the thing is, though, we can actually do better even with this technology, even with this level of sophistication, because if x is 0.1, suppose I never wanted an x bigger than 0.1, then I should be able to do a bit better on my estimate of m. So I'll just show a simple example of that. Let's say I happen to know that for my application, I only need to worry about x in the interval, let's say minus pi over 6, just to make things simple, to pi over 6. So about minus a half to a half, roughly. Okay. So in other words, d here is pi over 6. The half width, I shouldn't erase that, the half width of my interval. So d is pi over 6. And so I can look at, to get a new m, that's what that's going to allow us to do, is it says, well, we can get a bit better on the m. It's not going to be amazing. That's still absolute value sine x. Oh, when x is less than or equal to pi over 6, then that's going to be less than a half. So now, as long as we stick to this somewhat restricted interval near 0, but it's not a big restriction because we knew it was kind of crazy to go much beyond that anyway and get any kind of decent approximation, we're going to be able to do a half over 6, or 1/12. It's not a dramatic improvement here, but it is a nice thing to know that when you restrict x, you can get a better estimate for m, and and this is only for x in, we're only guaranteed that for x in this interval. Again, though, with error bounds, these are all inequalities. It's never saying that the error necessarily has to be even as big as this or as big as this. And sometimes the error is quite a bit better. And as I said, for cosine, there's some nice reasons why it turns out to be better. But that's a simple example of how that story would work. So let's go on. I want to show a little bit quicker this time. I want to show the cubic approximation, T3 of x. Let's just try to guess it and then check it, and maybe not be quite so careful about how to derive it. We're going to expect that we take the linear approximation, extend it to that quadratic approximation, and then add a cubic term, and you get the pattern here. It's probably going to be some factor times the third derivative at a only. That's the easy value. Again, this should be something that usually is going to be easy to calculate, times x minus a cubed. Okay, so I just need to know what that factor is going to be. Well, if you look at the pattern here, and if you think about derivatives, why was this a 2? It canceled the 2 coming down. When you differentiated twice, you got a 2 coming down and then a 1. When you differentiate this, we're going to get a 3, and then a 2, and then a 1. And we need to cancel all of those out. So that's called 3 factorial. Okay, so let's check it. I'm going to assume that you've checked that T3 of A and T3 prime of A and T3 double prime of A all match F, the appropriate quantities for F, and we're just going to calculate the triple prime. Constant, 3 derivatives kills that, long dead. Linear, 3 derivatives definitely kills that. Quadratic, 3 derivatives definitely kills that. That's the new bit. 2 derivatives turns this into a constant, namely exactly F double prime of A. 3 derivatives will kill it. 3 derivatives of this guy, okay, you're going to get that 1 over 3 factorial, F triple prime of A. Those are just constants. And then what happens if you take 3 derivatives of x minus a cubed? First you get 3 times x minus a squared. Then you get 3 times 2 times x minus a. Then you get 3 times 2 times 1 times x minus a to the 0, which is just 1. And this, of course, is what we want. Okay, so a little quicker version. So that suggests, yeah, we're really on the money here. That should be the third degree, or often called third order, Taylor polynomial. Best cubic approximation to this function. Indeed it is. And let me write it out even to emphasize that pattern, because that's going to make it, I hope, pretty clear what the total pattern is going to be. Very often when you've got something that is some sort of summation with a pattern, you want to make sure you write everything, even things that don't seem to need it, to fit the pattern. I'm going to make this a 2 factorial because it really was a 2 times 1. We differentiated this twice and got 2 times 1 and had to cancel that just like I said. This one is an x minus a to the 1 divided by 1 factorial. Actually, so yeah, I guess I'm just going to write it up here. And then I'll put it in sigma notation here. Okay, what about this guy? This really is, you could think of this as times x minus a to the 0 power and divided by, if you remember the convention for factorials, this is one of the many reasons why this is a really good convention. 0 factorial means don't multiply any numbers together, and the default for that, just like powers, just like something to the 0 power, is 1, not 0. So what we're getting is something where the pattern is absolutely uniform throughout all the terms. 1 over a factorial, derivative of f at a, and then a power of x minus a. So we could write this with summation notation or sigma notation as the sum k equals 0 to 3. I'm going to bring in a new dummy variable, an integer like k or n works well, or I, j, k, l. Something from the middle of the alphabet works well. 1 over k factorial, f, and then the kth derivative. Remember, that's the notation when you want to have derivatives of varying orders, including orders that are really high, of the function f. So that's going to be the 0th derivative. Oh yeah, we can write this as the 0th derivative of f, that's f itself, times x minus a to the k. This, if you plug in the different k's, this gives you exactly that. Constant term, the linear term, the quadratic term, and the cubic term. And the great thing about this, of course, is that we can absolutely guess, for example, what the quartic, or 4th degree, or 4th order Taylor polynomial is going to be. Exactly the same pattern. Not even a single change in symbol, but just take it to one more. The last term is going to be 1 over 4 factorial, the 4th derivative of f at a, times x minus a to the 4th, and so on. And we're going to have some things to say about the and so on. So, well, actually, let's just do it. Let's just do part of it right now. I claim if you have a desire to go really far to an nth degree polynomial that's going to be near a really good approximation to your function, and in particular, what makes it really special, very particular facts that make it special, is that this polynomial will share all of its first n derivatives with your function f at a. And so this would be, we're going a little bit out on a limb, guessing a little bit here that this is still going to work, but I hope the pattern is pretty clear. It's not too hard to see that this story is going to continue. So this is the nth degree. Again, degree is kind of the terminology when you focus on polynomials, or when you talk about how many derivatives you're taking. The word often is called order. Pretty synonymous here. Taylor polynomial at, of course, at a, and it all depends on exactly where you're using your base point. And this is going to be a good approximation near a, and it's going to be probably pretty terrible if you go very, very far away from a. So next time I'll talk about the remainder estimate for this nth degree or nth order polynomial, and then talk about what happens if you actually maybe change that to an infinity.